Alright, time for another draftphysics.com. Debate physics also. And so now and then there's something to debate, I suppose, but there won't be the necessary argument, counter argument, which, you really have to have, I think, for these conversations to evolve, progress and narrow and make more specific and more precise the arguments. But anyway, so this Al-Kahari guy, I don't think much of his physics, frankly. And, in a way, he's arguing against Richard Feynman's interpretation, and he won't say it overtly, which is sort of annoying. Because Feynman at least says, well, it's definitely not a wave. Okay, now it's doing this random thing, and there's all this quantum mechanical effects, but yeah, it's not waving. And they won't even argue with each other in some sort of honest way where they actually point out what physicists they are disagreeing with and all of that kind of stuff. And so it just muddies the water. And so this is back to photons, more specifically, I think. Okay. Because they'll claim that electrons do the same thing, and it's not the same experiment. It's a completely different experiment you do with electrons than you do with photons. So you shouldn't pretend it's the same experiment when it's physically not the same experiment. So, like I said, all this stuff just makes it harder to have a rational conversation because they're really just not very honest. So anyway, I don't think I need to play the video. We'll just go over some of the crap that is the fodder for the conversation of wave particle. Now, Franklin's a wave person for whatever reason. I think he thinks there's a superstructure of particles and that they're waving. So he's, again, recognizing that the wave isn't elemental. There's not some thing in the universe called a wave thing. Okay, there's stuff, and the stuff can wave. So he would be an etherist who thinks ether waves. Now, the argument against that, I would argue, is, pretty, frankly, from my perspective, decisive in the sense of, well, forget it. It doesn't go anywhere. All right, because the problem is, I have to do this, fix this stupid glare issue again. Sorry. Just should be even less time it takes me to do it, but it does take some time to do it for whatever reason. All right. So source and then target, and waves do this. All right. They have to spread over space, which means they have to get weaker and weaker and weaker, because you can't say, okay, it's going to spread over more surface and have the same intensity. How could it possibly do that? It starts off with a little bit here, and that little bit has to travel spreading in two directions. By the inverse square law, it's going to get incredibly weak with distance. So you can't even make sense out of this idea that a photon is being created as a wave front, because it would have to be self-aggrandizing. It would have to get stronger and stronger as it goes through space. And, it goes billions of light years, and it gets stronger and stronger and stronger. It's an insane amount of energy total that the one little photon thing, the one little perturbation had. That perturbation would have to, and so then you're stuck with this completely nonsensical idea that somehow, no, it has all this spreading energy, but it only lands in one place. So all of these little bits, all of this energy that was going this way or this way or this way, somehow appears here instead, where it lands. I mean, all right, you can make sense out of that? I can't. So maybe I'll give you the benefit of the doubt, because none of these people ever draw one of these things. They never draw a photon. Well, okay, I'll give you the benefit. All right, so you're not really arguing waves versus particles. You're arguing waves versus rays or something. So you're conceding it's a ray of light, and that somehow your wave is just this part. Okay, so it is a ray of light. Okay, it's just going through here. It's just waving this tiny little bit of space here. So now it doesn't have to lose energies because it's like a laser beam of light. Okay, it's a little laser wave. You know, a little laser wave. All right. Okay, well that at least that fixes the energy problem, so you don't have the same energy problem. But aren't you being kind of dishonest to say this is about waves and particles when it's really about rays versus whatever these things would be called in comparison? I mean, if we're going to say this is a wave and this is a wave, you know, then we have no vocabulary at all, right? I mean, this has clearly got to be a ray, okay? So, can we understand that, well, do you agree, you know, Franklin, do you agree that the waves are in the form of rays? So, can we at least recognize that this is the fact, okay, and that you're saying that the wave thing somehow in the ether is just this thing going through, you know, with some frequency, whatever that would be. The frequency would be made how? I mean, you know, what? How does it stay in these little tiny? How does your wave do this? How does it stay confined? You know, what? It doesn't make any sense to me. So yeah, so the mechanics falls apart really fast for me personally, in the sense that Feynman's correct, I think, in arguing that in all of these experiments you'll find out it's all kind of clumpy. That, you know, that's how the photomultiplier works. It's a clump detector. You know, that it does seem that clumps of light land in places. They land in, you know, locations that are, you know, not tiny but not big either. It doesn't land everywhere. So, you know. Alright, so I guess the first argument is they mess up the whole conversation by not dealing first with wave versus ray, and then deal with the fact that, yeah, I can make a ray out of bits moving at a frequency, alright, and account for the existence of a frequency by just saying they're bits, okay, and a red light would be bits further apart, and blue light would be bits closer together. Now, if I make it out of an ether, then obviously it gets kind of sloppy in terms of saying, well, how do you make the different frequencies out of some sort of medium that has a consistent, you know, matrix of whatever you think the ether is? How do you make that substance? First off, how do you make straight lines? Because this isn't going to be a straight line. Your clumps aren't going to be able to make straight lines in any direction. They're going to be bound by the checkerboard rule, you know, that you're going to end up with this weird diagonal thing that's much longer than this line, and that's going to screw up your physics. Can't really make the lines longer and shorter, the distances, how many clumps you hit, because clearly the photon that hits here and the ones that hit in all these different locations hit with the same properties. So that just doesn't work. Alright, so anyway, we will erase the board and go to the next argument. Just compiling some of the pieces to the argument, which again are just muddled. I mean, they're the physicists. They've had hundreds of years to put this together, and they all just talk a bunch of kind of, you know, just a narrow, they give you one little tiny piece of the argument, you know, instead of putting all of the arguments together and saying, well, look at, well, all these facts, what do we know? And so I'll state some of the facts that they just don't point out that, you know, are really kind of important. Alright, back. I guess I should point out, I'll put this video on YouTube, so I'll do a little bit of an update of the videos I made this week at the end of the video and such. Alright, so the stuff they don't say about electricity, which is really the way we measure photons, so and the way you understand all of these effects are some sort of electrical effect in a way. And it's really talking about ionization. So Franklin was using the argument that was basically the photoelectric effect. And the photoelectric effect is kind of complicated in the sense that you can describe it in more than one way for each circumstance, like what's actually happening to the surface. So one idea is you shine, blue light versus red light onto a surface, and a metal. And so it's always a metal. Always something that can convey electricity, a conductor at minimum. And the argument, and then you gotta have another experiment, frankly, that they don't point out that often, but he does mention it in the video, Al-Kahari, that you can have an electrical potential between, a positive and negative, and you can actually shine blue light in between the two poles, and you will enhance the creation of a spark, okay, the transmission of the electricity. So they're too far apart in regular atmosphere for a lightning bolt, so to speak, to jump the gap. But if you shine blue light between the gap, you'll make the gap. So this was, I guess, first noticed with the staircase thing, the thing that, where the electricity zaps up between the two sides and does all that stuff. Alright, back. So there are different ways to make this thing happen, and so the argument would be is that when you're causing this phenomenon on the surface, that you might actually be causing it, partially because of the atmospheric molecules. So I have to see how this works, in complete vacuum, and all of that argument can be made. That maybe all you're doing is creating ions in the sense that you're smashing the atoms into the surface. And some of this is true because of that little light detector thing, the little funny, photoscope or whatever they call it, radioscope or, whatever, the little spinning thing, because it doesn't work in a complete vacuum. It has to have some atoms. And, what's really happening is you're hitting the atmospheric atoms with the blue light, giving them enough velocity to smash into the surface and create an oxygen ion or a nitrogen or some other ion that's bouncing off the surface, and so you're taking the electrons away by smashing into the surface more vigorously. Now you could also obvious the blue light would be hitting the surface and creating ions on the surface that would have enough energy to pop off the surface, or not, frankly. They don't have to leave the surface. So you could argue that, see that you have so many different ways of, so many different pieces of evidence, right? Your little heart, okay, they've sort of found that what's happening on your heart is just ionization goes across the surface of the heart, causing it to beat. So, it just goes from being positive ions to negative ions, positive ions, negative ions, and that's what's causing the muscles to contract and the whole thing to work as a pump. And that's the electricity thing. So you could just argue that that's all that electricity really is, because even if it's a surface of atoms, the fact is that we think of ions as being free things in space. Here it's got an extra negative electron. We think of them as being, there's an ion flying through space, flying through the air. But no, an ion can be stuck still on the surface. And so you're really just talking about a surface that has too many electrons. And too many just means the electrons are directly communicating with each other. So you could argue that all the metals are already ionic. They're already ion heavy, and that's why they can conduct electricity, is because they already have too many electrons. Electrons are close enough together, okay, that you can communicate a push on one electron to all the other electrons. It'll move because the electrons are close enough together, and that's what works in the atmosphere for lightning. So a lightning bolt, not a very good drawing of one. It has to first create the ions, okay, they sort of found out, before it can move. So first off, it has to ionize the atmosphere before the atmosphere can be a conductor. So it has to pile up some extra electrons in the atmosphere between the two before it can now move the electrons by pushing them. So it's like you can't have a gap You need to fill, you can't have gaps, because then you push on this electron, it just fills that gap and it stops. So to have the chain reaction, so to speak, or to, all the people, it just has to be too many people, and then, you can't have an empty space and then too many people again, for pushing. If you're going to push and you need to keep going, well, you can't have a big gap in the pressure. And if you have a gap, the idea, like in an electrical circumstance, you have a gap. The idea is it has to put the electrons in the gap, and then it can complete the circuit. So it's always negative first, all right? Before you can have anything called electricity, you have to have something that's negative to start with. It has to already have too many electrons. There has to be more electrons than the average amount of electrons. So if you want to make electricity, you can't make it by showing up with a positive. You have to first have something negative to make it work. You can't just put in positive, because all that's going to do is charge something. It's not going to make it electrical. So to convey electricity, you have to have too many electrons. That would be the rule. The rule is it's conveyed easier, okay, by adding electrons, by having more electrons. So I'm just saying there's lots of different experiments. And then again, Feynman would describe to you the photodetector, and say, okay, we have all these metal plates, they're going to absorb reflections, you're going to bounce electrons through this system, and by bouncing them each time across a voltage potential, you're going to amplify their effects. You're going to keep speeding them up. So you speed them up, they create 10 electrons. Then you speed it up again, and over here it creates 100 electrons, and then you speed it up again, and you get 1,000, and it just increases at a higher rate than that, because it actually adds up to 1,000,000 times. You're amplifying one event into 1,000,000 times a strong event. So it's just an amplifier, you could say, the photodetector. And what's it amplifying is an ionizing impact. Something that's going to cause electrons to move and move off the surface. So you have to have too many, again, for them to fly off the surface with ease. If they're bound to the protons too rigidly, they're not going anywhere. And so they have to be movable in the first place. That's why they use certain kinds of metals that are electron heavy. They have extra electrons in a sense. They have a lot of electrons that are weakly bound and can be moved easily. Alright, so we'll do one more bit on this specific subject. I'm just saying there's a lot of physics here. There's a lot of, you can make a lot of arguments about what's really happening. And I could make the argument that anytime you're ionizing something, hitting it with ionizing radiation, you're going to change its electrical potential. You're going to make electricity, as long as the substance is a conductor. Alright, so this comes down to, okay, the two-slit experiment, different things where they talk about creating shadows, and that shows that it's waves, because shadows wouldn't be made by particles, when of course they could be, if you understand the particles are subject to being diffracted or deflected, okay, by surfaces. So none of these arguments are conclusive. But I think one of the arguments that was in the specific part that Franklin, I had played this Al-Kahari video, and I made the same observation about it being a pretty crappy example to be throwing golf balls at cans and then throwing whatever, Nerf balls, and saying red light is Nerf balls and blue light is somehow golf balls. That somehow it's more massive. When that's not the trick. The trick isn't that the blue light has intrinsically more momentum, because it doesn't. All it has is that you're doing this, right? You have more of these things, okay, in the same amount of space. And what's the trick there? Well, that gets to the whole resident thing. How do you put more energy into a system. So I've done this so many times, but physics just doesn't do this, and this is just so fundamentally important to understanding what's happening in any of these systems, is you put a little bit of energy into a system. You push this thing to this location, all right, and now it's going to swing back. All right, now that's your frequency. And you're arguing, well, okay, if I hit it with red light, this is all I do. You know, it moves to this location, and it swings back, and it swings back, and swings back, and it stops again. And that's all I'm ever going to get. Okay, no matter how much red light I throw at it, I'm not going to get this to go any further. And the idea is that you're really just talking about an electron being in space, and you could argue that it's tied loosely. And what you really want to do is break the string. You want to try to push it further away, where it's not going to go back. So you want to send it far enough from the magnet where it doesn't feel the magnet anymore. So you're just saying, if these were magnets, you know, if there's a certain amount of, I can move the I can move these two objects. So say they're this distance, this one shoots right into the other magnet, but there is a distance where it won't go back. Okay, it doesn't have enough energy to go back. There's not enough difference in the potential, whatever, however you want to describe it. There's not enough attractive force, and it won't come back. And so all you're really saying is that's the key point, is can you give it enough energy where you push it far enough away where it can't get back again. And that's ejecting an electron. And so in this argument, it's just kind of simple that, yes, if you want this to go further, you need to add the energy. So you hit it with the initial energy, and while it's still moving in this direction, you hit it again. Okay, so you could hit it again here, or you could hit it again here, or you could hit it again here. And what blue light is basically saying is that's the that's the one where you've made the difference, where you've showed up at the right frequency to say, I hit it again before it started going back. All right, so I gave it another boost of energy. So I pushed it further, and so I got it far enough away where it can't go back. It's not a pendulum anymore. I broke the string. The string broke because I gave it too much velocity. I added, so this is one velocity. This will be two velocities, two impacts. And that's, you've broken its frequency. And so the same argument could be said, you don't have to break it free, but you're just giving it enough energy to cause an event that can't be caused until you give it enough energy. You have to push it far enough to do something. And the fact is that you need more than one hit to make the event happen. So blue light makes the event happen because you have two hits within the required amount of time. So you're adding energy. So the point is, if it's coming back this way and you add the energy, the two will consume each other, and you'll get energy out in all kinds of other directions. The momentum will end up being lost to a bunch of other directions because it can't go in the direction it wants to go in, the direction it was going in. So neither one of these win, and all of these sideways motions win instead. So you don't gain anything. This doesn't go further this way. So, and that's the key point. So, I mean, there's lots of ways this can be argued and understood. All right, let me just do the slit argument one more time. I've already, I think, had this conversation with Franklin, but like I said, there's no back and forth, so there's just no point. It's just it's always a wasted response, I suppose, because there won't be any follow-up to any of the points made. All right, so the problem is that a lot of these arguments have to be made through analogies, and that's where the Al-Kahari guy really fails, is his analogies are pretty distant from the physical fact. I mean, throwing a blue ball and throwing a red ball that are different masses isn't really in any way relating to the fact that we know that frequency is the key component, and that doesn't show frequency at all. It doesn't have frequency as part of the equation. It's using mass to replace frequency, which is a huge cheat, so to speak. All right, so I can, so there's this idea that shadows get fuzzy, all right, because of an object, and the simple object is, the simple point is that somehow you can't make a physical particle theory fit that description. And I would argue, of course you can, by just understanding what kind of particle it is. Okay, that let's say light is frequency of some kind of little bit that's the smallest little bits in the universe, okay? Little tiny bits of momentum, little stuff moving the speed of light. And then magnetisms and electricity, all of it's made out of this little stuff. And the little stuff is what's causing electrons to hate each other, okay? The little stuff is bouncing back and forth between them, and the closer they get, the more the little hits happen. The further away they are, the less the hits happen. It perfectly fits with the inverse square law and all those rules, and it makes a good deal of sense. And so what happens when you shoot a bunch of light, which is a bunch of these little bits and patterns that we call light, a photon? Well, the little bits are going to hit the surfaces where there's a bunch of electrons. These extra electrons are always sticking out, right? The atom is made of a positive nucleus that's tiny, and then has these electrons out here. So the surface of anything, this is the surface, right? The surface is electrons. So the photons, the little bits, are going to travel through that sea of electrons, okay? And what's going to happen is that we already know they scatter. That's what happens when photons interact with electrons. They can go in all kinds of directions because the electrons have their own motion. So the electrons are vibrating, getting pushed around in space. So at one minute they're going this way, the next minute it could be going this way. So what happens? So what happens when the little bit hits an electron going this way, and it hits it? Well, then the electron's going to go some new way. And what's happening when the electron goes in a direction? Well, this is happening. It's pushing into the field of energy. It's going to collect photons and push more of them towards the universe. So it's going into the universe, and it's going to reflect the same little bits. It's going to reflect them as it moves. So every time an electron moves, it's pushing more little bits in the direction it's going, and less little bits are reflecting in the way it was. So you can understand the total universe as the little bits being light, okay, and the electrons being things you will see in the light. Okay, so the electrons and protons are things just reflecting light. They don't make any light. They're not like suns. And so you only see them when they move towards you. And they're gone when they're moving away from you. They disappear. So they're invisible when they're not pushing, and they're visible only when they're pushing, because they're sending more stuff to you so you could see them. So anyway, so that's simple explanation. Okay, photons are really small, the bits that make up the photon. The photon's big because the photon is a pattern of bits that has a polarization. Okay, and the polarization is proportional to the wavelength, the distance. So you're talking about something thousands of atoms in size when it's actually received. And that makes perfectly good sense, because how do we detect receiving it? Because it creates electricity. And what's electricity? Electricity is a pattern moving across atoms. So yeah, it makes sense. And what's electricity best understood? What's the key word is voltage and pressure. Okay, so the idea is increasing pressure or decreasing pressure, but you have to have pressure before you can decrease pressure. So you're still required to have the excess of electrons before you can take away electrons. But anyway, so yeah, scatter completely explains how the photon changes direction. So all the light that goes here and here and here and here becomes that fuzzy edge to anything you're shadowing. So you can put something here and say, look, I created a fuzzy edge to the shadow of this object. You know, the shadow is less precise. Well, yeah, because you're deflecting a bunch of photons on the surfaces. They're not going straight anymore. Okay, they're going some other direction. Alright, so a particle model can't answer the question without any, you don't need to jump into any kind of woo space to make this simple argument, and that all you're really doing is taking the scatter you create on all these surfaces. For the double slit experiment, this works perfectly. You just take the scatter from all these locations and you say there's a 50-50 chance, okay, that you're going to be in phase or out of phase, that this distance will be longer or shorter, you know, by the required amount. It's either going into phase or it's going out of phase. And that's a 50-50 chance that the number's getting closer to a full wavelength in phase or a full wavelength out of phase. And that decides whether or not you're going to reconstruct a photon, which is reconstruct the frequency. And so you either will be reconstructing the frequency, or you'll end up with something where they're not reconstructed. Let's say it takes minimum of 4 little hits. This pendulum works on 4 hits. You have to hit it once, and then twice, and then let's just say 3 times. That's your frequency. And you either have 3 things hit in that time cycle or you don't. But the point is there's a 50-50 chance you're going to put these photons will land on a surface in phase or out of phase. So the whole surface is getting hit by the same number of the little bits. And understand the fringe pattern, okay, the bulk of the light just goes straight through and lands here. That's 90% of the light is there, okay, within 1 millimeter. The fringe, the pattern you see, is made out of only a tiny percentage of the light. A small percentage of the light creates the fringe pattern, and all of those photons had to come off of a surface. And again, if you do the math for the forest surface experiment, then you'll get the overlapping patterns. The widest distance, okay, between 2 surfaces perfectly accounts. You have a pattern that will look like this. Okay, so you have a pattern that look like this. There's 2 patterns here, right? There's the spacing between these little dots, and then there's this missing dot, and then there's this. And so you have 2 patterns. You have the envelope, and then you have the regular pattern inside the envelope. And 4 point sources accounts for it by simply understanding you have the widest distance between 2 surfaces. And so this has the most potential for a wavelength difference. You can have a wavelength difference here. You can have a wavelength difference here. You can have one here, 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 here. You can have lots of wavelength distance because you have a lot of distance between these 2 points. So if you just mathematically figure out what this distance is, divide it into the wavelength of the light, you'll know exactly how many of these little nodes you have and what their spacing are. So the little ones, the little spaced dots, are made by the biggest distance, and then the smallest distance, which could be this distance or it could be this distance, doesn't really matter, but the smallest distance is the one creating this. Okay, in the sense that it has a lot fewer locations, because the closer you bring the 2 points to each other, the fewer lines you can make that have a wavelength of difference. So these clumps are on because half the light is coming from this close distance and half the light's coming from the furthest distance. So when both of them, when you're on phase here and you're on phase from here, you get a dot. When one of them's off, when you're off phase from here or off phase from here, then you get this empty spot. And that's the simple explanation, that it's only on when all 4 sources are producing a bit. The 4 sources have to make a bit going to the location for you to see the photon. You can't make it without the extra energy coming from the other 2 sources. Any 2 sources aren't creating enough photons to make the pattern. So you're only going to see it when all 4 make a contribution. So anyway, it works. It's a perfectly reasonable explanation. And I would argue the particle model works for so much of the rest of physics. It works because it involves a thing called momentum. It's really easy to understand. It's mass and velocity. That argument that the velocity for forces is always the same, the speed of light. The mass of the particles, yeah, well, that's always the same too, the speed of light. And all you're saying is how many particles are hitting. And the most important part is at what rate, at what timing are they hitting, because everything is a resonator. Every single object in space, every atom, has a frequency you can hit it with that matters. That's why, so I could go to microwaves and why they affect water. Because certain frequencies are going to be the frequency that you're most likely to put energy into the object, because it's going to make it, it's going to bounce at the right rate. So you hit it with a piece of energy, and you can push more energy in before it goes back the opposite way, and then you can keep adding energy. So if I push it and then it goes back and I push it again just at that right point, now I've got twice as much energy. I've got the reflection plus the energy I added, so now it's going to go twice as fast, and then each time I hit it, it'll go 3 times as fast, then 4 times as fast. So it's going to make the little bits move faster and faster because I'll keep adding energy to the system. So whatever the system, the oscillator is, all the oscillators have a frequency that they like in the sense that it'll make them oscillate faster, and frequencies that will make them oscillate less quickly because you're adding the energy opposed to their oscillation. Alright, that's probably enough of this. But it's physics, and frankly, you can't do these subjects, by throwing 2 of the facts together and then making your argument. You really do have to try to put all the facts on the table, all the different circumstances, and then say what fits all of the circumstances, not 2 of them, but all of them. And nobody's doing that. I can't even do that, frankly. As one person, I can't compile all of that and do. I mean, it takes real devotion to the subject, and physics isn't bothering to devote anybody to those subjects, and that's too bad. Alright, so we'll do a little bit of reviewing and call it a video. Well, I guess I should point out there are some kind of funny comments here. The Brozo shows up, and look at this. I'm posting links separately in case links are blocked. So that's some new post 5 days ago. I didn't see it before. The only bit I'm suggesting may be slightly relevant is from about blah blah blah. Some of my demonstrations of diffraction of particles and total internal reflection and the so-called triple polarizer paradox. So yeah, it's just all nonsense because he thinks it has something to do with Lenz's law. Sorry, no hope. Often cited as some quantum weirdness phenomenon, but easily demonstrated as having much, let's see what he says, simpler cause with microwaves here. Alright, well, we'll have to go look at that later. Over here, he just nags some guy about what's the definition of a lie. So this guy shows up, he's a wave fanatic, and he's saying, oh, how dare you listen to this asshole talking about it not being waves, because it has to be waves. Yeah. And then, so they just keep arguing about the dishonesty. Well, there is a standard for the dishonesty. I mean, when Al-Kahari says the electron experiment is just like the double slit experiment, when it's not. So, I mean, that's a lie. It's a lie to say it has something to do with 2 slits when, no, you're shooting the light at a matrix of a crystal. It doesn't have slits in it. It's not 2 slits. It's a crystal with different layers. I mean, it's a completely different experiment. To call it the 2-slit experiment is lying because it doesn't have any slits in it. I mean, that's really just breaking the rules, right? That's a lie. It's just wrong. I mean, it's, again, to say a ray and a wave are the same thing is a lie. Come on, it's just stupid. So, you got to call bullshit somewhere. So anyway. So they're both full of shit. I obviously have no horse in this argument about whether or not you can call it a lie. But Brozo throws the word around like it's nothing, so it's just very funny. How is that dishonest? He just keeps asking. How's it dishonest? How's it so? Where's the honest? Why can't it be an honest mistake? What's honest about? There's no way you have an honest mistake where you call a crystal, that has layers, a 2-slit experiment. I mean, that's just too preposterous. It's not 2 slits. It's not even 1 slit. It really isn't a slit experiment. It's a different experiment. It's got to be called a different experiment. Anyway. Alright. So I'll move on. Soon. Alright, back. Alright, so yesterday's video, okay, was basically on, it's called Speed, Energy, and Such. And it's kind of a complex subject, just in subtle, small ways, but it's making this simple argument that electrons work different than big matter. That the key is just momentum, but you have to understand what momentum is to an electron and what it is to some big giant object that has a bunch of atoms in it. And the two things are doing two different things. No, they're doing the same. They're doing the same thing. There's just a simple difference between what happens to them. So to understand why there's a speed limit, you just understand that the speed limit is the pushers. The pushers are the only thing that makes the electron move. So it gets hit by a pusher. It sticks, the pusher, and it continues to push it. And that's what it requires. And I can have more pushers, and the more pushers I add, I can never go faster than the pushers are going. They're all behind me, pushing me if I'm going. So I can only go as fast as they can go. So even if I had 1,000,000 of them behind me, I still don't have any push. So I still weigh something and they have to all carry it. And so it just means that this is slowed down by less an amount. So if one of them hits me, it's the force. The little force bit was going the speed of light. It hits me. It's got to push me. And I weigh as much as it does. Well, then you could figure it's going half the speed of light. Alright, so the force bit, the pusher, is now going half the speed of light. The more pushers that help him, the more this number changes. I go faster and faster. But as you can understand, I can never go faster than the pushers are pushing. So I'll do the Lorentz thing. But for the big matter, the difference is that I can hit it with one tiny piece of the same force that pushes one electron 1/2 the speed of light. So electron gets hit, it goes half the speed of light. This big giant object that could weigh 10 tons gets hit, and it's not going half the speed of light. That's not going to happen. All right, you have to divide the one little piece of momentum, the little tiny mv. Well, it's a big V, but it's a very tiny m, so tiny that I couldn't even draw it. And it has to basically spread it over its entire mass, and it does that by basically just time sharing. So the pusher, I have all these different atoms and all these different electrons and protons, and what has to happen is the pusher, okay, pushes this one a little bit. Then it jumps to this one, pushes this one a little bit, and then jumps to this one, pushes this one a little bit, and then jumps to this one. Theoretic jumping, The idea is that it's all time sharing. The force is going to be blended into each other because there's force between the electrons. Obviously, I hit it with this one. The other electrons are going to know this one got hit. So basically, the energy of the one little push is going to be time shared across the entire object. So over a period of time, the one little pusher, okay, will do a certain amount of pushing per second. And so, yes, my speed is going to be incredibly slow. I mean, one little tiny force bit over, say, 10 tons, it's going to be like, 1 foot every 10,000 years or something. But the fact is, it's in there, and it is doing it. It's just going to take it a long time to move everything, for everything to finally move in that direction, for the little tiny bits of movement to convert into a visible movement. But it's exactly the same. The mechanism for both is the same. It's just understanding that this one's doing it directly and this one's doing it indirectly because of time sharing. That was in the video, and to some extent, you have to look for it, but it was there. Alright, this was a comments video. I don't think it was worth much, but just to point out that the comments are never on the subject. There's no point. People don't really want to argue the argument. They want to argue your history. You didn't go to college. You didn't do this. You have no right. Blah, blah, blah. All this kind of bullshit. So the arguments, fuck the arguments. It's all about your standing or your, you're not allowed to have an opinion, apparently, unless you've been elected to Congress or something. So it's just horseshit. There's no useful debate. And I did a couple of videos, I think a couple of them anyway, sort of related to the LINAC, or the linear accelerator, and why they're basically saying, look, we're increasing the power, the momentum of stuff landing, but we're not increasing its speed, and theoretically we're not changing its mass. So how can we give it more momentum if we don't change its mass and we're not changing its speed? So clearly the speed doesn't increase of the particles. They're already going close to the speed of light. So if I can't increase their speed to give them more momentum, how can I create something that has 10 times more power, yet it's not going 10 times faster? Then I have to say, well, its mass increased. I can say it, but I won't be able to prove that. And I would argue that the mass of the object hasn't increased. The mass of the stuff you're pushing it with has increased. Oh, yeah. I got to put this back. Yeah, my mistake. Not that it's important, but to see the picture of the Linac guy. But anyway, that's what the video was about. So I had talked about this video before, about the fact that they're not really, measuring the temperature of something isn't a very direct way to measure the energy. But anyway, it's a whole nother subject. So this was more comments, and it ended up being, the lever arguments obviously right here. Right here I'm probably arguing Stephen Bro did the experiment, frankly. He proved the levers do create free energy by his definition. If you accept 1/2 mv squared, you have to accept that levers make free energy. They take the same amount of force, and you're able to make twice as much or 4 times as much or 10 times as much energy just by sliding your mass further and further down the lever. So you can make any amount of energy you want, theoretically, which obviously is nonsense. And I've obviously now made the pressure argument, which is even more obvious, about cylinders. So I'm sure that was in here somewhere. Yeah, we did some gyroscope talk, and the most obvious thing about gyroscopes is you just say to yourself, how does anyone communicate with a gyroscope? The wheel is spinning in space. How are you communicating with it? Well, obviously you're communicating with the piece of metal shoved up its butt, that's rotating on. The bearings is how you're communicating with it. And obviously if you push up, you're going to go sideways. You can understand that it's a wheel rotating, and you're just deciding where you're going to put the road. Do I put the road, wheels rotating this way. I put the road here, I can put the road here, I can put the road underneath, I can put the road in all kinds of locations. What's going to happen when I apply that road? Oh yeah, the wheel's going to go in that direction. So it's just recognizing where the bearings are being, where there's more impact on the bearings, and that impact has to go through the bar, and that has to go through your hand, and it has to go through your arm. It goes through your whole body. So you're just moving the torque by applying pressure on the bearing. The bearing is essentially an interior road, okay, that's not any different than if you had a road on the outside. If you had a road that you could move on the outside, you could understand the wheel's going to go no matter which way I hit the surface, whatever way it's spinning. I just figure out which way it's spinning, it's going to go that way. So if I push it this way and hit the road here, it goes that way, right? It's just not that complicated. And I'm surprised that people come up with all these ideas that the rotation is something, and this is and it's spinning the ether and all kinds of, no, none of that crap has to happen. Alright, I'm sure this was the pressure argument. Here's the cylinders. You connect 2 cylinders, you push, it's just as simple as if I compress a space with 2 things going 5 miles an hour. Or I just have one of the walls move at 10 miles an hour. I'm doing exactly the same thing. They have exactly the same amount of total energy or capacity to make pressure. So it would be nonsense for me to think that something going 10 miles an hour has twice as much energy as twice as much mass moving 5 miles an hour. Because I can make free energy by just using a pressurized vessel and having one cylinder push in here. We'll have 2 cylinders push in on this side at 5 miles an hour, and I can make one cylinder go 10 miles an hour. So I can make free energy. I can make something that's calculated to have twice as much energy with something that has half as much energy. That can't be correct. It can't be possible. If free energy was possible, we'd already have it. For fuck's sake, you got to know that. So, so it's not within the range of you're gonna. If there's going to be free energy, it's not going to be this obvious and this simple. It's going to have to require you to squeeze it out of something, you know. So it's just such bullshit. You're not going to squeeze it out of a lever or a piston all by itself. So yeah, that's the gyroscope. Yeah, so that's probably enough of hitting the subjects. There's the pressurized. It's just so simple. These walls moving in. The 1/2 mv squared can't be correct because simple experiments prove it's impossible. It doesn't work. It creates free energy. It can't be the right answer if its outcome is you have a source of free energy. So it should be an argument that's over. I shouldn't have to keep arguing it. It should be a reasonable concession by reasonable people that yes, 1/2 mv squared wasn't very thought out very well. It wasn't tested. It didn't go through the rigorous process that science should require before you make something a law or make something an edict. It doesn't deserve the badges you've given it. It was just a counterculture kind of pile of crap. It was just some sort of anti-Newtonian nonsense to throw into the space because a bunch of people's egos were hurt. And it just doesn't make any rational sense. Let it go. Alright, so that's probably enough of a video. So yeah, there's 5 or 7 videos on the website since the last video I posted here on YouTube. And they all have some merit. You know, some are just rants, but you know. I am human and must argue from my human perspective on occasion. So anyway, till the next time and such. This has been a draftphysics.com debate physics, but again, you really have to debate through a process of some sort of logical process where you have to stay on the subject and you know, you really do have to get to some point where you understand what you're really debating. Are we debating waves versus rays? Or are we actually debating moving, you know, stuff moving from one place to another, like physically moving? Or are we just talking, you know, are we required to believe in ether? I don't think there's anything requiring us to believe in an ether. I don't think there's anything indicating that space has to be filled with some sort of crap for something to happen. No. You don't need dominoes. You just flick the domino and make it go where you want it to go. You don't need it to bang into a bunch of other dominoes to get there. Anyway, till the next time and such and so forth and whatnot.